Hey everyone, and welcome to this explainer. Look, if you're staring down the barrel of a high-stakes AI or machine learning interview, you are in exactly the right place. Today, we're completely cracking the code on the model building lifecycle, and we're doing it specifically tailored to the questions that actually come up in this really rigorous technical interviews. We're going to walk through the entire roadmap together, from messing with raw data all the way up to tuning complex deep neural networks. Let's get into it. But before we get totally lost in the technical weeds, keep this quote in mind. Albert Einstein basically hit the nail on the head when he said, if you can't explain it simply, you don't understand it well enough. You see, AI interviews aren't just about proving you can crunch the math or write some Python code. They're really about proving you can clearly communicate complex trade-offs to stakeholders. If you try to just hide behind math jargon, trust me, interviewers are going to catch it immediately. You have to be able to tell the story of the data.
Okay, let's dive into this. Here is our chronological journey for today. 1. The AI interview landscape. 2. Taming messy data. 3. The Bias-Variance Trade-off. 4. Classic models and ensembles. And 5. Deep learning demystified.
Starting off with Section 1, Taming Messy Data, Setting the Foundation.
So imagine you're sitting across from the hiring manager, and they hit you with this high-frequency question. How do you actually handle missing or corrupted data in a data set? You know, there's that old joke that data scientists spend 80% of their time cleaning data and the other 20% complaining about cleaning data. It's funny because it's true. Real-world data is notoriously messy. Sensors fail, files get corrupted, people skip questions on forms. You literally can't just feed that raw garbage into most algorithms. So what's your plan of attack?
Well, you've essentially got 3 main plays here. First, you could just simply delete the rows or columns with missing values. Sure, it's fast, but you really only want to do this if it's a tiny percentage of your data. Otherwise, you're just throwing away valuable information. Second, you can lean on algorithms that natively handle missing values, like k-nearest neighbors or random forests. And third, which honestly is often the best approach, is data imputation. This is where you estimate the missing values using the mean, median, or mode. You can even use a separate machine learning model to predict what that missing value should be based on the rest of the data. Like, say, predicting a missing salary value based on the person's age and their job title.
Right. So once your data is actually clean, you have to figure out the relationships within it. And that brings us to this absolute classic statistics question. Explain the difference between Pearson and Spearman correlation. This tests your foundational knowledge of how data points move together, and I promise you, an interviewer will expect you to know exactly when to use which. What this brilliantly illustrates is that correlation really isn't a one-size-fits-all concept. Pearson evaluates linear relationships using the raw data values, meaning it needs a constant rate of change. Think of Pearson like 2 people walking perfectly in lockstep. If one goes up, the other goes up proportionally. Spearman, on the other hand, evaluates monotonic relationships using rank-ordered variables. So think of Spearman like 2 people simply walking up the exact same hill. They don't have to take the exact same size steps, just as long as they are both consistently moving upwards.
Moving right along to Section 2, the Bias-Variance Trade-off, the ultimate balancing act.
Look, if you are sitting in a machine learning interview, there is literally a 90% chance you're going to hear this exact question. What are bias and variance, and what is the trade-off? If you stumble on this or can't explain it clearly, it is a massive red flag for the interviewer.
So let's break this down without the textbook jargon. Bias is essentially when your model makes overly simple assumptions. It's like assuming every single problem is a nail just because all you have is a hammer. It drastically oversimplifies the problem. Variance, on the flip side, is when your model basically overthinks the specific noise of your training data rather than learning the actual underlying patterns. It gets completely distracted by all the tiny details and totally loses the big picture.
So the absolute crucial point you need to hammer home in an interview is how these two fight each other. A high bias model, like a simple linear regression, is probably going to underfit. If you use it to predict house prices, it might just broadly miss the actual market values because, well, it's just too simple. But a high variance model, like a massive neural network, might overfit. It might perfectly memorize the weird quirks of the specific houses in your training data, but then the predictions will vary wildly when looking at a brand new neighborhood it's never seen before. The ultimate goal of any engineer is finding that perfect sweet spot right in the middle.
All right, Section 3, Classic Models and Ensembles. Time to choose your weapon.
When you're staring at classic models, the big question is always, when do I go simple versus complex? Let's consult this cheat sheet. Linear regression is beautifully simple and super efficient to train, right? But is it reliable if your data is extremely noisy? Probably not. Support vector machines, or SVMs, are absolutely fantastic for high-dimensional data and nonlinear problems. but can you afford the incredible compute time required when you have massive datasets? And what about decision trees? They are wonderfully easy to explain to non-technical stakeholders, and they handle nonlinear problems seamlessly. But of course, they are highly prone to our old friend, overfitting. And because overfitting is pretty much the ultimate villain here, interviewers will immediately ask you how to fight it. Enter this fundamental question: what are L1 and L2 regularization, and what are the differences between the two? Both of these basically add a penalty to keep the model simple. But now what's really interesting about this slide is how different their actual mechanics are. L1, which is also known as lasso, penalizes the absolute value of the weights. This actually forces some coefficients all the way down to 0. This means L1 acts as a built-in feature selector. It literally drops completely irrelevant variables entirely. L2, or ridge, penalizes the squared weights. It prevents any single parameter from getting too huge and taking over the whole model, but the weights never actually hit 0. It just keeps everything nicely smoothed out and in check.
Okay, stepping away from individual models, we run into the ultimate ensemble face-off question. What are the similarities and differences between random forest and gradient boosting? Both are incredibly popular decision tree-based ensembles, but their foundational philosophies are completely different.
So random forest leans completely into the wisdom of the crowd. It uses a technique called bagging to build multiple trees in parallel, perfectly independent of one another. Think of it like asking a highly diverse crowd of experts for their independent opinions and just taking a majority vote. It gives you a highly robust prediction that is way less prone to overfitting. Gradient boosting, conversely, relies on boosting. Think of it more like having one expert write a draft and then the next expert specifically focusing on fixing the typos and mistakes of the first sequentially. It can achieve mind-blowing accuracy, but because it hyper-focuses on those specific mistakes, it's far more prone to overfitting if your data is full of noise.
Let's move to Section 4 and see how this all builds up. Deep learning demystified, facing the final bosses.
Now we are in the big leagues of modern AI, and the questions? They get super specific. Take this terrifying sounding but incredibly common issue. What is the vanishing gradient problem and how do you fix it? If you're building deep neural networks, you are absolutely going to encounter this during backpropagation, and you need to know exactly how to diagnose it. Okay, here's the under-the-hood explanation. During training, neural networks update their weights using the chain rule, multiplying derivatives backwards through all those hidden layers. Think of it like a giant game of telephone. As the message passes backwards through many layers, the signal gets weaker and weaker as those tiny fractional numbers are multiplied together. Eventually, the gradient effectively vanishes. By the time the update reaches the very beginning of the network, the earliest layers essentially freeze up and stop learning entirely.
Thankfully, you have a solid checklist of fixes you can deploy for this. First, you can use skip or residual connections. This is the magic behind ResNets. Think of these connections like adding express lanes or highway bypasses that allow the gradient to travel backwards without getting stuck in all that local traffic. It completely bypasses the vanishing issue. Second, swap out those old sigmoid activation functions for ReLU or leaky ReLU. They don't squash the gradients down nearly as much, which allows the signal to stay strong. And third, if you're working with sequence data like text, rely on architectures specifically designed to propagate gradients effectively over time, like LSTMs or GRUs.
Next up is one of those highly practical what would you do scenario questions. Your deep neural network is strongly overfitting the training set. What can you do to reduce it? This is directly testing the depth of your practical troubleshooting toolkit.
In an interview, you want to rapid-fire these mitigation strategies. Number 1, the easiest fix. Just get more data. Or artificially augment what you currently have to force the model to generalize better. Number 2, utilize early stopping. Literally, just pull the plug on the training process before the model starts memorizing the noise. 3, apply the L1 or L2 regularization we talked about earlier to penalize those large weights. 4, introduce dropout. This randomly turns off neurons during training so the network can't rely too heavily on any single pathway, forcing it to learn redundant representations. 5, use batch normalization to keep your layer input stable. And finally, if all else fails, just reduce the model complexity. Honestly, maybe you simply don't need a network that massive to solve the problem.
To wrap up this explainer, let's look at something a bit more philosophical. Hiring managers know that just reciting technical facts isn't enough anymore. They often ask this: what is the most sophisticated ML concept you know, and how would you explain it to a newbie? Your answer to this reveals everything: your technical depth, your ambition, and most importantly, your communication skills. Don't just learn the math, learn the narrative. If you catch yourself giving the exact same answer to this question year after year, well, maybe it's time to learn something new. Thanks for joining me on this explainer. Keep learning, and I'll see you next time.